Hi everyone, we're going to talk about Unit 9 of the AP curriculum in this video and introduce some of the first concepts that come up in that unit. One of them is entropy, and if you look at this picture here, you can see that it has to do with processes like burning a match. Why does, for instance, a piece of wood burn, but a pile of ashes never turns into a piece of wood? Why does fruit rot, but rot never fruits, so to speak? And of course, you could reason that some of these things do in fact happen in that counterintuitive direction, that rot in your compost turns back into fruits in the right circumstances, and even ashes sprinkled into your garden will turn back into a piece of green wood. But some of these processes are not thermodynamically favored, and a key idea as to why some processes are thermodynamically favored and occur spontaneously, so to speak, and others are not, has to do with entropy. We will define entropy as the dispersion of matter or energy, and a more technical definition of entropy is much more complex, but we can simplify things for the purpose of this course and think about entropy as simply the dispersion of matter or energy, and that's going to suit our needs just fine. As we go through this unit, we're also going to talk a little bit about the laws of thermodynamics. The first one is often stated as energy cannot be created or destroyed. The energy of the universe is constant. And we've thought about this when we were studying thermochemistry. For instance, we drew some energy diagrams for exothermic or endothermic reactions, and you should be able to tell whether this one that's shown here is exothermic or endothermic. And we talked about the fact that any heat energy that was lost by the system was transferred to the surroundings, and vice versa. Heat energy that was transferred to the system must be depleted from the surroundings. I want to remind you also that when we drew those energy diagrams at the beginning of the year, we did not look at that part which is in purple here, which has to do with kinetics. We only looked at the difference in energy between the reactants and the products, which we call the change in enthalpy. In thermodynamics, when we want to evaluate whether a process is thermodynamically favored, we don't need to consider the reaction pathway. That's really the domain of kinetics. So we can simply look at the changes in the system between the reactants state of the system and the product state of the system. But in addition to evaluating enthalpy changes, we're also going to want to evaluate entropy changes. Our objective is to predict which direction a process will be spontaneous in. In other words, which one it will be thermodynamically favored in. And the word spontaneous, although it's used commonly in this context, is maybe one we should avoid because that seems to suggest that these processes are instantaneous or happen quickly, whereas spontaneity of a reaction in this context really just talks about whether it is likely to happen without outside energy. So we'll use the words thermodynamically favored or thermodynamically unfavored instead of spontaneous and non-spontaneous. A thermodynamically favored process is one that will occur without outside assistance. For instance, water evaporating at 125 degrees Celsius, that is spontaneous or thermodynamically favored. Examples of non-spontaneous processes are water boiling at 1 atmosphere and 75 degrees Celsius. That's not a spontaneous process. It's not thermodynamically favored. It should make sense that any process that is thermodynamically favored in the forward direction will be unfavored in the reverse direction. For instance, water freezing at 263 Kelvin, that's a spontaneous process or a thermodynamically favored process. So the big question is, how can I tell if a process is thermodynamically favored or not? It is true that exothermic reactions generally are more likely to be thermodynamically favored processes. There are many endothermic reactions which are as well, such as the evaporation of water, you'll remember, is an endothermic process. So we need to look beyond enthalpy in order to answer this question, and it's going to involve analyzing entropy as well in order to determine what's called the Gibbs free energy associated with a process. There are 3 rules we're going to use to evaluate whether or not a process is spontaneous. And I'll sometimes say spontaneous just because it's easier to say than thermodynamically favored. But again, thermodynamically favored is preferable because the word spontaneous implies quickly. A process is spontaneous if the change in the entropy of the universe is positive, or the change in the Gibbs free energy of the system is negative, or if the equilibrium constant is greater than 1. Now you may remember that the equilibrium constant is temperature dependent, but at a particular temperature, if K is greater than 1, that means we're talking about a product favored equilibrium. And so it should make sense that the equilibrium constant is one way that we can evaluate whether a process is spontaneous. You'll notice the other two are new terms that we haven't introduced yet. The term S is the symbol for entropy, and the term G is a symbol for Gibbs free energy. It might be good to explore the concept of entropy with a few other examples that may illustrate why the universe tends towards a system of higher entropy. If I throw a deck of cards into the air, the chances of them landing on the floor, like is shown on the left picture here, is very unlikely. That's a highly ordered system, and it's one of trillions of different arrangements the cards could land in. It's much more likely statistically that they're going to land in one of the high entropy states on the right. Another example that's commonly used is a clean room versus a messy room. Of course, a clean room is a highly ordered state. There's only one arrangement that corresponds to a clean room where everything's in its place. There are many different arrangements for a messy room, and so it makes sense that statistically the messy room arrangement is just more likely. The second law of thermodynamics applies here. You'll notice that the word entropy is right there in this articulation of the second law. It says in any spontaneous process there is always an increase in the entropy of the universe, where the universe is defined as the system and the surroundings together. So essentially this is saying that the universe tends towards disorder, and that's an important governing principle that the second law of thermodynamics implies. We can also mention the third law of thermodynamics, which relates to entropy here as well. It says the entropy of a perfect crystal at absolute zero is zero. Entropy increases with the temperature of a system. For instance, let's consider water vapor, where matter and energy are highly dispersed. If we cool the vapor so that it condenses into a liquid, that's a slightly less dispersed state of matter and energy. And if we continue to cool it until it forms a solid, that's a much more highly ordered state. In other words, a very low entropy. And if we continue to cool that solid and form a perfect crystal where there is absolutely no disorder, then theoretically we'll have a system where the entropy is zero. So let's go back to the second law of thermodynamics. It says that in any spontaneous process, there's always an increase in the entropy of the universe. And it's true, we're going to use subscripts like universe, system, and surroundings there. We're going to define, like it shows at the bottom of this slide, the universe as the system and the surroundings added together. Well, let's practice evaluating the change in entropy for a particular system. See if you can pause the video here and predict the sign of delta S for each of the following. Remember, if the sign of delta S is positive, that means entropy of that system is increasing, and if it's negative, then it is decreasing. So a positive delta S means a more entropic system, or a more disordered system. The evaporation of alcohol, since we're talking about something going from a liquid to a gas, is turning into a more disordered system, where matter and energy are more dispersed. That's an increase in entropy. The freezing of water, conversely, is turning a system into a more highly ordered system. In other words, one where matter and energy are less dispersed. Compressing an ideal gas at a constant temperature, well, that's going to be a decrease in entropy. If we compress a gas, it's going to become more ordered because matter is less dispersed as the gas particles are closer together. If you heat an ideal gas at constant pressure, then you're increasing disorder because energy is more dispersed as the temperature increases. If you dissolve sodium chloride in water, we're starting off with a sodium chloride crystal, which is highly ordered, and we're resulting with ions in aqueous solution, which is more disordered. So that's an increase in the entropy of the system. So we've learned that entropy is a measure of disorder of a system. And we've also learned that a greater degree of disorder is favorable. You may remember in the fall we would calculate the enthalpy change for a reaction by looking at the standard enthalpy of formation of the products and the standard enthalpy of formation of the reactants. We can do the same here if we want to know the entropy change for a reaction. We look up the standard entropy of products and reactants, and we can calculate the entropy change associated with the reaction. Here's a good practice problem for us to look at. See if you can calculate the standard entropy change for this reaction. Now you need the equation that I introduced in the last slide, which is also on our purple papers. It's just like the enthalpy change equation, products minus reactants. Don't forget to include the coefficients when you're considering the calculation. And if you pause the video now and see if you can try it out, then you can unpause it and see if you get the answer that I'm going to show here. You should get -11 joule per Kelvin. So we've practiced determining the entropy change for a system, but in order to determine whether a process is spontaneous, we also need to know the entropy change of the surroundings. So let's talk about how we'll evaluate that to figure out whether this value is positive or negative. Remember, if this value, the entropy change for the universe, is positive, in other words, if the universe is becoming more entropic, then we know it's a thermodynamically favored process. We've now evaluated the system. How are we going to evaluate the surroundings? The entropy change of the surroundings really depends on whether a reaction is exothermic or endothermic. And we're only going to consider heat flow at constant pressure, which simplifies things a little bit, but it should make sense that for an exothermic process, the surroundings are going to become more disordered because heat is flowing into the surroundings and causing a greater dispersion of energy in the surroundings. So this equation shows that delta S of the surroundings is equal to a negative delta H over T. Remember, for an exothermic process, delta H is negative, so that means delta S of the surroundings must be positive. The sign of the delta S of the surroundings depends on whether the process is exothermic or endothermic, the direction of the heat flow. And again, if you look at that equation, which is in blue, you'll see it makes sense. For an exothermic process, delta S of the surroundings would be positive. For an endothermic process, delta S of the surroundings would be negative. So keeping that in mind, let's take this for a test drive and evaluate a simple process. The process we'll look at is just liquid water turning to gas. We want to evaluate the change in entropy of the system, the change in entropy of the surroundings, and as a result of those two determinations, figure out what the change in entropy of the universe is. Remember, if the change of entropy of the universe is positive, then that means it's a spontaneous process. Well, first let's evaluate the change in entropy of the system. The change in entropy of the system we can think of, if we're turning from a liquid to a gas, that simply means we're turning to a more disordered or more dispersed system where matter and energy are more dispersed in the gas, so the entropy of the system is increasing. How about the entropy of the surroundings? Remember, that depends on whether this is an exothermic or endothermic process. Do you remember whether turning a liquid to a gas is exothermic or endothermic? Let's see. To turn a liquid to a gas, we'd have to add energy to the system. That means depleting the surroundings in heat energy. And if you deplete the surroundings in heat energy, then the surroundings are going to, that means that the entropy of the surroundings is negative. So what can we conclude about the entropy change for the universe? Well, you know that for a liquid to turn to a gas, that's a process which is only going to be thermodynamically favored at certain temperatures. And it makes sense that if we want to evaluate the entropy change of the universe as being the sum of the entropy change of the system and the surroundings, and if one is positive and one is negative, then it's going to be a temperature-dependent process. So this is the first of three ways we're going to be practicing how we determine if a process is thermodynamically favored. The first one is whether the entropy change of the universe is positive. The next video will look at Gibbs free energy, which is another way we can determine whether a process is thermodynamically favored.